All right, so this is lesson 2.2 from chapter 2, really the first lesson for unit 1, and it's entitled The Derivative the Fast Way. So by the end of class today, you should be able to find the derivative using something called the power rule. So first of all, we have the constant function rule. So how do we find the derivative of a constant? If we think about the definition of the derivative, it's the slope of a tangent. If we have a constant function like y equals 5, if we were to sort of sketch a graph of that, y equals 5 would be up here. At any given point on that line, no matter where we draw a tangent, it's going to have a slope of 0. So that's what this means up here. So if the function is a constant value, the derivative is 0. That will always, always, always be true as long as it's a constant. Now, as I mentioned in the lesson 2.1, this is a different notation. So we're saying the derivative of the constant with respect to x has a value of 0. So that's that Leibniz notation that's going to keep cropping up throughout. Now, the power rule. We have done a lot of different functions where we have expanded, simplified, and then figured out what the slope of the tangent expression was. So if we were to take f of x equals x squared. What the power rule is telling us is that the derivative, so f prime of x, I'm changing the notation to show that I'm getting the derivative. The exponent comes down in front, so that gives me a value of 2. X is going to stay there because that's the defining part of my function. And then the exponent decreases by 1, so we end up with a value of 1. When we were looking at the graphs of functions and their derivatives, we noticed that the power always decreased by 1. So if you started off with a quadratic, you ended up with a linear function in terms of the tangent. If you started off with a cubic, you ended up with a parabola in terms of the tension. In terms of the tangent. So when we're looking at it here, we see 2 comes down in front, it decreases by 1. So the function has the tangent equation for its slope to be 2x. If we do the proof for one last time, so f prime is the limit as h approaches 0 of x plus h, put that inside of a bracket because I'm substituting in, minus x squared all over h. Okay, so then we're going to have equals. I still have that limit as h approaches 0, x squared plus 2xh plus h squared minus x squared all over h. So this is going to give me the limit as h approaches 0. The x squareds go away. I'm going to factor out that that h. So then I'm left with 2x plus h all over h. I substitute in, I get a value of 2x. Way more efficient to use the power rule where the exponent comes down in front. So that's sort of basically the power rule, and it'll make your life way, way, way quicker. So now, here's a bunch of examples. So we just looked at that one. So the notation becomes f prime of x equals 2x. Done. Finished. Before, that would have been a 4-point question. Now it's worth 1. All right. G of x. Before I actually get the derivative here, I'm going to rewrite my root so that I have it as an exponent. So the square root of x is the same thing as 1/2. So this becomes g prime of x. I'm changing my notation. The exponent comes down in front, so that's 1/2 multiplied by x. If we subtract 1 from 1/2, we get negative 1 over 2. We don't like exponents in our numerator, so this becomes 1 over 2x to the power of 1/2. You can leave it like this, or you can rewrite it as 1 over 2 square root of x. Either situation is the same. If we look at this example over here now, we have a coefficient out in front. So how will that impact our value? So h prime of x is going to equal, the negative 5 is going to stay there. The 4 comes down in front, and then it becomes x to the power of 3. So this gives us an overall derivative of negative 20 x cubed. So any coefficient that is being multiplied by your variable, you're going to incorporate it by multiplying the exponent and that value together. Now this one right here, I'm going to rewrite it as 20 x to the power of 1 over 3. So now we're ready to do the derivative. The 20 stays. We're going to multiply by 1 over 3. And then x, the exponent that we're going to have is going to be 1 over 3 subtract 1. So we get negative 2 over 3. So this becomes 20 over 3 x to the 2 over 3. So that would be our derivative. Now, how would we use this? We would actually get a value for x, substitute it in, and that would be the slope of the tangent at any particular value that we're looking for. So we're going to complicate them a little bit more by looking at the sum and difference. So all we're looking at now is if it's a composite function, meaning there's more than one term. So polynomials will be our main target here. How are we going to work with that? So this expression is telling us that the derivative of the first plus the derivative of the second. So very straightforward. We're just going to break it up into pieces. So our example, so y equals 2x squared minus 4x plus 6. So differentiate the following means get the derivative. So y prime, the derivative of 2x squared is 4x. The derivative of negative 4x is going to be minus 4. And then the derivative of 6 has a value of 0. So you'll notice, because there's a constant there, one part of the derivative is 0. I'm not going to write it because it's redundant. It just has a value of 0. Now the next one, f prime of x, so I'm following the notation that's kind of started. The 3 comes down in front, so 3 multiplied by 27 is 81. X to the power of 2. Then we're going to have minus 2 multiplied by 2 is 4. X. This is going to be plus 3 multiplied by 1 over 2. And it's x to the negative 1/2. I'm actually going to fix that. It looks a bit... Oh, okay. Let's rewrite that. So we're going to have 81 x squared minus 4x plus 3 multiplied by 1 over 2 multiplied by x to the negative 1 over 2. And then the derivative of 5 has a value of 0. I have one last step to do here because we don't like negative exponents. We'll have 81 x squared minus 4x plus 3 over 2 square root of x. Now, this last example on this page, before I can actually get the derivative, you need to expand this out. So when we expand this out, we're FOILing. So we get 1 minus 2x is minus 4x plus 4x squared. Later on in this chapter, we're going to learn another rule here that we can use so we can avoid doing the expanding. But right now, our toolbox only has the expansion. So when I expand that out, so this is an equal sign. So 1 minus 2x minus 4x plus 8x squared plus 4x squared plus 8x cubed. So this is going to become 1 subtract 12, not 12. So this will be 1 subtract 6x plus 12x squared plus 8x cubed. You'll notice I haven't changed my initial notation at all. So now I'm ready to change it. So y prime equals 1. I'm going to erase that 1 because the derivative of 1 is 0. So the derivative of this one has a value of 0. Then I'm going to have minus 6 because the derivative of negative 6x is minus 6. 12 plus 2 is 24, so plus 24x. And then this will be plus 24x squared. So this expression represents the slope of the tangent of that 1 minus 2x all cubed function. So if we have a value of x, we can substitute it in and get the specific value of the function at that point. So not very difficult. Here the hardest part was actually doing the expansion so we could use our power rule. Now, this one right here, again, I'm going to simplify it because we don't have a formula for a rational expression yet. We will be getting one a little bit later on, but for now, I'm going to simplify it. This means q is divided into everything. So this becomes 5q squared plus 2 minus 3q to the negative 4. So I use my exponent rules. Now I'm able to actually do the derivative. So 5q squared, the derivative is going to be 10q. The derivative of 2 is 0. And then we're going to have plus 12q to the power of negative 5. So I got my last cleanup step. So 10q plus 12 over q to the power of 5. And then that would be the kind of answer that I'm looking for. So again, right now, for a question like this, you want to simplify it so that you have a composite function where you're adding and subtracting multiple things. All right, so this question back in chapter 1 took a lot of work because you had to use your limit as h approaches 0 in order to figure out the slope of your tangent. However, much more efficient now. To find the equation, you need two things. We need a point, which we have, and we need the slope. And we know our slope is equal to the derivative. So an expression for our slope will be 6x minus 2. The 2 comes down in front to give us 6, subtract 1, that's why the exponent changes. Same thing, 1 comes down in front because that's the exponent, we get negative 2, and then there's no x left over because it has a power of 0. So now, since it's a value where x is 0, so I substitute in, so I get negative 2. So we know our slope, y equals mx plus b. 1 equals negative 2 multiplied by 0 plus b. So 1 is equal to b. Therefore, the equation will be y equals negative 2x plus 1. So way, way more efficient than it was in the last chapter. I think that's the last example we have for this. Oh no, one more. So it's asking to find or determine the value of the derivative when x is equal to 1. So again, before we do anything here, I'm going to simplify this. So h of x, I'm going to divide. So basically, if I show a little step here, this is going to sort of justify a little bit more where my final exponents are going to come from. So we get 2x squared minus 3 plus x to the power of negative 1. I'm going to fix that. So plus x. 1/2 subtract 1 is negative 1 over 2 minus, I don't want to have any x's in the denominator. So if I move this x up, I get a value of negative 1. Now I'm ready to get the derivative. So h prime of x. So this is 4x. The 3 goes away. Minus 1 over 2 x to the negative 3 over 2 plus 1 x to the negative 2. Before I substitute in, I am going to simplify it again. So we get 4x minus 1 over 2 x to the 3 over 2 plus 1 over x squared. Now that our derivative is fully simplified, I can substitute in my value of 1. So we get 4 multiplied by 1 minus 1 over 2, 1 to the power of 3 over 2, plus 1 over 1 squared. which equals 4 minus 1/2 plus 1, which equals 5 minus half, which equals 9/2. So that was the last example. Hopefully it makes sense. But the key thing is the exponent always comes down and then decreases by 1.